I will not be recording this كده. ماشي. اللي عايز يصور يصور. I will not be recording it. So anyways, we'll start إن شاء الله. I will not be recording this, so if you want to take pictures or whatever, no problem. So we'll be doing some problems today, solving some problems. Let's start. ممكن everyone concentrate please. يا بنات let's concentrate. خلينا نركز كلنا بقى. اوكي تمام. لا في اهو هو اسود بس. Okay. So let's start with the first problem. So for a binary symmetric channel واحنا الباينري symmetric channel بنسميه BSC. Okay. With error probability equals P. تمام. Find the entropy of the input to this channel. ده أول سؤال. Okay. طيب. So to solve this, the question. So answer. You start by plotting the binary symmetric channel اللي احنا we looked at it already during our slides. تمام. So how does the binary symmetric channel look like? It has a source that generates either 0 or 1. تمام. And this is the destination or the final target of this channel. And the final, what's received on the other side can be either a 0 or a 1. تمام. And if what was transmitted is was 0 and what's received is 0, then this is correct reception, right? So no error here. And if what was transmitted was 1 and what the receiver sees is 1, this is also correct. Okay. Errors happen if the transmitter sends 0 and the receiver by mistake reads this as a 1. This is an error case. Or the other error, if the transmitter was sending a 1 and the receiver by mistake detects that as a 0, that's another case of error. And the error probability is P for the symmetric channel, both 0 to 1, 0 to 1 or 1 to 0 errors have the same probability, which is this probability P. So we have here, this happens with probability P, this happens with probability P. تمام? This error happens with probability P, this error happens with probability P as well. Now if this is the case, if what was transmitted is 0, there are two situations for receiver. The receiver does a correct decision, so it detects 0, or it does a wrong decision and it detects 1. So error decision. تمام? This happens with probability P. Then this must happen with probability? Exactly. So this has a probability 1 minus P. Similarly here, it's 1 minus P. خلاص? With all this information, can you calculate the entropy of the source? What will be the entropy of the source? Expression ايه؟ Expression بيقول entropy is defined as ليش معنى 1 minus 2p؟ Okay. The entropy can be defined as what? What was the definition of the entropy? Yeah, which was defined as what? Summation of what? أيوة. Minus summation of what? P of symbol I multiplied by log to the base 2 P of I as well. What is P of I? Probability of what? Yeah. So the probability of the P was the probability of the symbols coming out of the source, right? So with this information that we have right now, we cannot yet solve for the entropy, right? The probability P that we have here has to do with the channel, right? The channel making an error or not making an error. It's not the source probability of 0 and 1. The entropy is more tied to the source itself, right? The entropy is not tied to the channel at all. تمام? So with this information, طبعا انا مش هجيب لكم سؤال كده, بس the target of me doing this, I'm not gonna get you a question like this because this is not a complete question. Okay? The only answer here is that I don't have enough information to calculate the entropy of the source. Okay? But the reason that I stopped here, okay, and I discussed it this way just to emphasize, when you are calculating the entropy is a property of the source. So you need the probabilities of the source producing 0 or 1, not the probability of error. The probability of error has nothing to do with the entropy. Okay? If you want to calculate the entropy, you need what's the probability of the source producing 1, what's the probability of the source producing 0. تمام? So what I will do here is I will complete the question. I will remove this. Okay? And I will complete the question. Find the entropy of the input to this source, knowing that the distribution of probability for the source is probability of 0 equals, let's call it PS. If this is the case, then you immediately know, now the question stops here, right? Now the source can produce only a 0 or a 1. So if we know what's the probability of the 0, which is PS, then the probability of a 1 is equal to 1 minus PS. So now you can start solving. Okay. Answer. So you would tell me from the source distribution, right? PS, which is equal to probability of 0, then P of 1 is equal to 1 minus probability of 0, which is equal to 1 minus PS. لأن الsource عنده only two possibilities, to produce a 0 or a 1. It's a binary source. And if I know that the probability of a 0 is PS, then the probability of a 1 is 1 minus PS. تمام? Now I have the full distribution of the source. I know what's the probability of producing 0. I know what's the probability of producing 1. Now I can apply the entropy equation. H for this source is equal to the summation over I, where I is, what is I? I takes the possible values of the source, right? So the summation over the case of 0, the case of 1, if the source has more possible outcomes, the case of 2, the case of 3, and so on. In this case, it's the case of 0 and case of 1. The probability of that case, Pi, تمام, multiplied by log to the base 2, either 1 over Pi, or you put a minus sign here, and you make it again Pi, which when you expand it becomes the probability of 0, which is called PS, تمام, P minus outside, okay, the probability of 0, which is PS, log to the base 2, the same probability of 0, PS, plus the probability of 1, 1 minus PS, مظبوط, log the same probability as well, 1 minus PS. وشكرا. This is the entropy of the source. خلاص? So the idea of this question is, if you get a question similar to this, you just need to know where is the relevant information. The P that I gave up, the probability of error, is totally irrelevant for the entropy. What you really care about is the source probabilities. The probability of the source producing a 0, the probability of the source producing a 1. If it was not a binary source and was something that can produce, for example, 5 outcomes, then you need the probability of the first outcome, the probability of the second outcome. If you have 4 of them, you can deduce the third, the fifth, because it's 1 minus all of those, right? Okay? So now knowing these probabilities, you plug them, because these are the probabilities of the different symbols coming out of the source. You plug them into the entropy equation and you get an expression for the entropy. خلاص? And instead of giving you PS, I might have given you a number. So you will solve and you get an actual number at the end. Okay? Any questions? خلاص? No questions? Be careful. Yes. Yes. Okay. No questions? Move to, for the same question, I can ask you, right? So I'm gonna make this in a new slide. So for the same question, remember that we had the probability of error, so I will plot just to remind you of the situation. So we have, 0, 1, 0, at the destination, 1, right.
What did you call this again?
Which one?
This like diagram.
Binary symmetric channel, binary symmetric channel, okay? And here we have PS, here we have 1 minus PS. These are the probabilities of the source symbols. And here we have P, the transition probability of error, and P, the probability of error as well, and 1 minus P here, 1 minus P here. Tamam? Now I can ask you, find the channel capacity for this binary symmetric channel. Tamam? So for finding the channel capacity, what do you need to do? Everything starts from the definition. Tamam? What was the definition of the capacity? So see, this is again question.
It's the maximum information you can have without error.
Yeah, so that's the definition qualitatively, but in terms of calculations.
What's the equation?
Yeah, so you will have the equations. I mean, in the exam, you will have your book with you, so you don't need to memorize equations. But I will remind you. So channel capacity C was defined as the maximum of the mutual information between the input to the channel and the output from the channel. And the maximization here was carried over the probability of the input, right? Which is this. So this is the distribution of the input, right? So we take all possible values of this distribution, all possible variations of this distribution, until we find the one that gives us the maximum mutual information. Okay? So eventually, the outcome from this equation is not gonna be a function of this. Remember this discussion last time, right? Because we already vary this across all possible values. So for example, you will say, let's assume that, of course, this is not how you are gonna solve this problem, but I'm just telling you what is the meaning of varying this, okay? If we put PS equals to 0.1, then this is 0.9. If we put this equal to 0.11, then this is 0.89, right? 0.89. If we put this 0.01, then this becomes 0.99. So you have to test all these variations until you find the one variation here, the fixed value here, that will give you the maximization of this. So before doing that, or in order to do that, you need to get this as an expression of the input probability. And then to find the maximum value, you take the derivative and equate that to 0. تمام? Let's look at what was the definition of I. What was the definition of I of x semicolon y? A reminder, x was simply to represent what's the input. So this is x, right? And y is the output. So this is y. Okay? What was the definition of I of x or y? You had two ways to calculate this, right? Either you say it's h of x minus h of x given y, or the same thing, it's h of y minus h of y given x. Both of these will give you Ix, the mutual information between x and y. Okay? Which formula you use? The solution for this problem will take a while. So I will not solve it until the end. But I'm telling you, there are two formulas, and we will go a little bit through the derivation so you know how to get h of x, how to get h of x given y, and so on. Okay? But we'll not do the full derivation here. Okay? But there are two ways. You can either calculate it from here or from here. And one of those is much, much shorter to get to the answer. Okay? The other one will take you very long derivation to get the answer. Okay? خلاص? So one of these, both are valid, right? Both apply to the definition of the mutual information between x and y. Okay? But one of these will make the solution much easier. We're talking here about the solution of finding eventually the capacity. Okay? So let's try to look at, first of all, initially, which one we have its information. Do we know what's h of x? That's the entropy, بس. No maximum here. H of x is the entropy of x, right? We have just calculated it, right? So we know how to express this, right? So first, if we look at the first expression, right, h of x can be easily calculated. We've just calculated it, and it was eventually what? Minus ps log ps plus 1 minus ps تمام log to the base 2 1 minus ps. We just calculated it in the previous part, right? So we have h of x. How do we get h of x given y? Can anyone remember what was the definition of h of x, the conditional entropy?
I'm not sure.
No. It was a summation and like similar to this. But it included inside it things that are different from p of x. This one is p of x log p of x, right? But this one is the joint probability multiplied by log the conditional probability. You remember this or you don't remember? Anyways, you don't need to remember it, but you can look it up in your slides, okay? So this guy, we are talking, sorry, about this conditional one. So let me do it this way. Okay. Is defined as the summation over all possible values of x and all possible values of y, right? Possible values of x and y means x0, y0, x0, y1, x1, y0, x1, y1. You have to go across all those four terms, right? Okay. Of what? Of the joint probability of x and y multiplied by log, of course there's a minus outside, multiplied by log to the base 2, the conditional probability of x given y. That's how we define h of x given y. تمام. So now you need to figure out the joint probability of x and y, and you need to figure out the conditional probability of x given y from the information that you have in the joint probability of x and y. Remember your probability course? I will So that's one approach. I will leave it for you. Try to complete solving this. You can find a solution on the internet. You can ask ChatGPT to solve it for you. Find the channel capacity for the binary symmetric channel. It will give you the derivation. تمام? So I will leave this for you to continue solving it using this formula, right? And then don't forget also to try to solve it using this one. And try to figure out which one is easier. خلاص؟ لا خلينا ما نتكلمش على الكويز دلوقتي، الاكزام دلوقتي. خلينا بس نفinish this وبعدين نتكلم على الاكزام. اوكي؟ So we can just التايم بيجري، فخلينا نيوز التايم وايزلي وبعدين نتكلم على الاكزام بعد كده، مفيش مشكله. اوكي؟ So this is one problem, the binary symmetric channel. Let me remember what other problems I want to do with you. طيب. Let's now look at this problem, okay? So for wire tab channel, okay? The connection between Alice and Bob is a binary symmetric channel with error probability equal to, we call it PC. تمام? That's the confidential channel. C stands for confidentiality. That's the one between Alice and Bob. While تمام the channel to the Eves اللي هي Eve يعني is another binary symmetric channel with error probability equals to PE. تمام؟ okay. Find the worst case scenario secrecy capacity of this channel اللي هي defined as equal the capacity of the confidential channel minus the capacity of the Eve's channel. تمام؟ capacity of the confidential channel معروفة طبعا is max زي ما عرفناها قبل كده يعني مفيش فرق over source distribution of I x semicolon y and the capacity of the Eve's channel equals max برضو over source distribution of I x z. Here is the kind of the system block diagram يعني عندي Alice and Bob. I have Eve. تمام. This is the confidential channel. This is the eavesdropper channel. تمام. So what's received here is what we call Z. What's transmitted from here is what we call X. What's received here is what we call Y. Okay. Notice that I gave you here the definition. يعني بس quickly كده an important note. Notice I gave you here the definition of the secrecy capacity, which is slightly different from what we had in the lecture, because that one is quite challenging to solve for. That one was actually maximum of the difference between those two, or maximum the difference between this mutual information and this mutual information. So it becomes a complex maximization problem. So to kind of reduce it, you just need to calculate the capacity of this, and subtract them to get the worst case scenario secrecy. And I will tell you why this is a worst case scenario. Tamam? Why we call this a worst case scenario. Question is, in order to solve this question, which I forgot to do in the previous slide, you need to know what was the final answer to the previous case. Because you need to know what's the capacity of the binary symmetric channel, since we are using it again here, right? And if you solved everything in the previous problem and was able to do the maximization and get to the result, you will find that for a binary, I will write it on the side here, for a binary symmetric channel, the capacity is equal to 1 minus h of p. Tamam? What is h of p? H of p, where? Is the function which is defined kind of very similar to the entropy. It's minus p log to the base 2 p minus 1 minus p log to the base 2 1 minus p. Tamam? So for any binary symmetric channel, if you know what's the error probability, tamam, p, immediately the capacity of that binary symmetric channel is given by 1 minus this expression. So it becomes 1 plus. تمام؟ عشان هنا في minus و minus. Don't forget that, okay? Okay? طيب. Now knowing this, tell me now what's gonna be the secure capacity or the worst case scenario secure capacity of this channel اللي هي secure channel هنا. Answer this question بقى. So this is question 3. ها answer بقى. Very simple يعني. Just equation اهي. This is the equation. You just need to figure out what's CC and what's CE. And here's the expression for C of any binary symmetric channel. So you just need to plug this expression into the case of the confidential channel, where the probability of error is PC, and for the case of the leakage channel or the eavesdropper channel, where the probability is called PE. صح? So, so if we want to do it step by step, you would tell me CC is equal to?
1 minus h of p.
Yes, 1 minus h of PC, right? And CE is equal to? 1 minus h of PE. تمام? We know how to expand this. أهو. This is how to expand it, right? So you can expand this and you will get, and the final result is going to be what? CS is equal to this minus this. So the 1 will disappear with the 1 and you end up with? Yes. So minus h of PC plus h of PE. Type. Okay. Nice. So far, and then if you substitute the log into this expression, you will get a nice expression with logs and stuff like that. تمام? Very good. And that's the end of the solution. Now we will elaborate a little bit more into this question. The next part of the أولا في any questions here؟ تمام. The next.
بالنسبة للإكسبريشن بتاع ال HP اللي احنا المفروض احنا بنعرفه من البروبابيلتيز ولا؟
تعرفوا منين؟
يعني الإكسبريشن بيبقى موجود أصلا في السؤال ولا احنا
اللي هو ده؟ لا ده أنا given. أنا هي rather than writing C بتساوي 1 minus P log P مش عارف ايه, we take all of this and we call it HP. فأنا مش هقول لكم HP ده وانتوا تحفظوه لوحدكم يعني. No, not at all. Okay?
worst case scenario.
Why it's worst case scenario? It's worst case scenario because what we did is rather than maximizing the difference between those two, we assumed that the eavesdropper is working at its best possibility by maximizing its rate, right? So if it's working with its own capacity, right? So this means that we have the strongest possible eavesdropper. So that's an analysis of the worst case scenario because you might have a little bit weaker eavesdropper, which will give you actually a CS greater than this. So this is kind of a lower bound on the secrecy performance.
So what about the CC? Is it also in the maximum strongest?
Again, maximize, yeah, but CC is by default to maximize the difference between those two quantities. You will definitely try to maximize this and minimize this, right? If you want to get the maximum difference between this quantity and this quantity. What is the best way? I'll try to make CC the maximum possible, which is the case. We keep it as maximum, right? And I will try to keep CE as minimum as possible so that the difference between them becomes a larger number, right? But what we did here is we kept this as maximum as possible and then we took this as maximum as possible. So that's why we call it a worst case scenario performance, okay? So the CC, we did not change the behavior. We always try to maximize it. But the CE, if we solved with the regular definition, we should have been trying to pull it away to make the difference as great as possible. But we didn't do that. We made it also as large as possible. That's why it's a worst case scenario analysis.
Would it be worse, like more than this, if the CC was minimum?
Yeah, but why would I do this? فاهم قصدي? It doesn't have a meaning. I'm just weakening my signal without really working towards the target that I want to achieve and without having a meaningful scenario for this. Okay? For the other case, I'm assuming that I design my system. If I want to design a system, what should I do? I design the system for the strongest possible attacker. If I manage to protect against that attacker, I will protect against all the other weaker ones. Okay? Okay. So this is why we call this a worst case scenario analysis. And we use it because it's easier to calculate. We just get the capacity and take the difference. In the other case, we would have stayed with I and I subtracted from each other, and then the maximization will be outside. So maximize the difference. And solving that problem is harder. Okay? Anyways, this is up to getting an expression for CS. The next couple of questions are going to be kind of a little bit qualitative. They are not quantitative. So they do not really need you to calculate something, but rather understand how this secrecy capacity works. Okay? So first, let's call it question 4. Okay? For the above, okay, discuss the effect of I having PE greater than PC and double I PE less than PC. So PE is what is the probability of error on the eavesdropper channel, right? Now, remember, okay, in order for this system to work and have some non-zero, it cannot be, there is no such a thing like negative rate, right? Okay, so to have non-zero, if it's negative, we assume it's 0 because there is no such a thing like transmitting with -3 bits per second. You cannot do that. Physically, it's not, means 0. You cannot communicate, okay? So for this to work out, you need this difference to be something greater than 0, right? So you need CE to always be smaller than CC. If it's equal or greater, you cannot communicate securely. The system is totally out of security. تمام؟ طيب. Now let's look at PE and PC. If PE is greater than PC, it means which channel is worse? The eavesdropper channel or the confidential channel? PE is the probability of error.
Yes.
If the probability of error is greater,
Then the confidential has an issue.
then the confidential is better or worse? Probability of error on the eavesdropper channel is a larger value. This means the eavesdropper channel has more errors. This is a weaker or a stronger channel? has more errors.
Condition is stronger compared to the Eve.
Confidential, yes. So I was, okay. So when PE is greater than PC, this means that the eavesdropper channel is weaker than the confidential channel, or the confidential channel is stronger than, right? So in this case, case I, the answer now, for I, we will have possibility to communicate securely. Okay? Case double I.
Security will be weak.
No security at all. If the eavesdropper is stronger, which means its probability of error is smaller, you cannot communicate with the confidential party or with Bob securely, because your rate of communication for secure communication is going to be 0 or less, which means no communication. Okay? So for case double I, secure communication is not possible or impossible, because in that case CS will be smaller than or equal to 0. Okay, and here if we want to justify, here we say because CS is greater than 0. Cannot be equal, huh? It has to be greater than, so that you can communicate. If it's equal to 0, you cannot communicate. Okay, so for the first case, CS is greater than 0, so you can communicate. For the second case, secure communication is not possible because the eavesdropper has a stronger channel than, okay, the confidential channel, so secure communication is not possible. That's the essence of that secrecy capacity, right? We calculate that quantity to figure out for this particular setup, can we communicate securely or not? Now the second part of this kind of qualitative questioning as well is going to be, so question number 5. Okay. In case 2, what means here? Give an example. So let's write it in a more, give some examples on modifications or techniques to enable secure communication. Okay, answer to this. What are possible techniques or variations to this system, or things that you can implement in this system to enable secure communication again? So by default now, the channel itself, you found that your channel with the trusted party, that's the natural channel, you did not touch it or you did not apply any techniques yet, was weaker than the channel to the eavesdropper. For example, you are communicating with a node which is far. That's the secure one or the confidential one, while the eavesdropper managed somehow to be closer to you, right? In that case, what can you do? We gave some examples in the lecture, remember? Yes. So one way is to try to jam. So the whole essence of the answer here is to try to implement a technique that makes the eavesdropper channel weaker than the other one. One technique is to jam the eavesdropper. So jam in Eve direction. Or the other is encryption, right? Because like encryption using shared key with, of course, shared with the trusted party only, huh? With shared key, right? Both of these are gonna make the channel of the eavesdropper weaker than the channel of the trusted party, and you can restore secure communication again. خلاص؟ أي أسئلة؟
أنا عندي سؤال بس مو في هاي اللي فوق.
يس تفضل.
شو الفرق بين اللي احنا سويناه والماكس اي اكس؟ يعني انت ذكرت ان الثاني more complicated، بس شو الفرق بينهم؟
طيب for this one يعني if we want to solve اللي هو to solve for the actual CS equals max over the source distribution, right, of I x y minus I x z, تمام, and the maximization of this whole thing, right? In order to solve this, you have to go and deduce IXY, YXZ, and find them as a full expression of the source probability. يعني كأنك as if you are solving the problem of the binary symmetric channel that we did before, but now with two terms, not just one term. تمام? So you'll have to repeat the solution from scratch. Find an expression for IXY, YXZ as a function of PS, اللي هي probability of the source, and then take the differentiation of that with respect to PS, equate that to 0, find the value of PS that gives you the maximum of this full expression, and then plug it into the equation to get an expression for secrecy capacity. Okay? And it's not going to be equal to this. No, they will not be equal to each other. Because again, just by logic, to maximize the difference between two quantities, this is not equal to taking the maximum of the first minus the maximum of the second. Definitely it's not. صح? But what we did here is we took the maximum of the first, اللي هو maximization of this only, and we took the maximum of the second, the maximization of this only. If you want to maximize the difference between two terms, this is not equal to the maximum of the first minus the maximum of the second. The max operator does not get into, you cannot take it into the expression. تمام? So that's why they will give you, but the solution here requires long derivations from scratch. Okay? Any other questions? I'm not gonna ask you to do something like this. Okay? And that's too much. Okay? حتى, by the way, just again, a hint. What I talked about in the previous part when we were trying to do the capacity of the binary symmetric channel. The solution that we did, that we were going through, is the long solution. If you go through the second expression, you will not need to do almost no derivations and no differentiation even. It will be just logical. This term, based on the logic of the channel, is equal to this. And to make this maximum, the first term is independent, the second term is dependent, so I only need to maximize the second. And the maximum of the second is already well known. So it's going to be like 3 or 4 steps, and you solve the problem. Okay? So, but I gave you the exercise so that you know that there is such a thing. Okay? Before we close, I need to do 2 things, but we have reached 3:12. If you want to stay with me for 10 minutes, there are 2 things I want to do. I want to solve one more problem, but more numeric, so with values, okay? And slightly easier than those ones, but still valid problem that you can get in your exam. And the second thing is to tell you something back about the binary symmetric channel. Just some nice ideas about it, okay? So, it's okay with everyone? Tamam. Let's go to the example, which is kind of, I would say, an easy example. For the additive white Gaussian noise channel. Sorry. Or the wiretap additive white Gaussian noise channel. We have واير تاب اللي هي التشانل اللي فيها أليس بوب إيف، دي اسمها واير تاب شانل. اوكي، واتقالت في لو رجعتي للسلايدز، اخر سلايدز عدينا عليها هتلاقي موجوده فيها الاكسبريشن ده. اوكي، for the wire tap additive white Gaussian noise channel we have SNR. Okay, call it C equal to 3 dB as the signal to noise ratio between Alice and Bob. Okay, while SNR E is equal to 0 dB as the SNR to Eve. Okay. Find the worst again case scenario, secrecy, capacity, knowing that Shannon capacity for additive wide Gaussian noise channel is C equals log to the base 2 1 plus SNR. Okay, and we call this the Shannon capacity, call this the Shannon normalized. I'll tell you why we call it normalized, but doesn't matter now. Okay, so this is how you find the capacity for any additive wide Gaussian noise channel. The problem that we are describing here is question 6. Okay, the problem that we are describing here, again, we have Alice, we have Bob. Okay, and this channel has an SNR C, and it is an additive wide Gaussian noise channel. So the whole wiretap channel is additive wide Gaussian. And this channel for Eve is also AWGN, additive wide Gaussian noise, and it has an SNR called SNRE. Okay, SNRE is 0 dB, SNRC is 3 dB. Knowing the SNR of any channel, you can find its capacity using this Shannon capacity expression. Okay, and what we are looking for is CS, the worst case, which is equal to CC minus CE. Okay, so we just need to plug the numbers, but we need to plug them correctly. You cannot plug dB inside log. You have to take it back to a ratio. SNR is a dimensionless quantity. It's a ratio of power to power. So you have to take it back to its original expression as a ratio, not as a dB, right? So you will, just a reminder, what was the SNR in dB is equal to 10 log to the base 10 of SNR as a pure ratio, right? So what we have is this, and what we want to find is this. So you can simply find the SNR in both cases by applying this formula, SNR. Now this, in this case, not dB, is equal to, what would you do? Divide the other side by 10, and then to get rid of the log, you raise 10 to the power. So it becomes 10 to the power of SNR dB divided by 10, right? This is how you get the ratio SNR from the dB SNR, okay? So we can figure out now, use your calculator please, and tell me what is going to be SNR C. And I tell you from now without a calculator that SNRE is equal to 0 dB. معناها ايه؟ معناها الريشيو inside the log is equal to 1. So this means SNRE is equal to 1. صح؟ To give me 0. To give me 0 dB, ما هو. So it must be that the SNR without dB is equal to 1. The other one بقى SNRC. Can anyone do it on the calculator and tell me what's the value? 10 to the power 3 divided by 10. لأنها in dB is equal to 3. تمام؟ 1.995. متأكدة؟ Okay. 1.995. Okay. I think this is approximate, right? So there are some more.
Yes.
Yeah. Okay. So that this is SNRC and SNR. Now this is the answer. Now we are trying to answer. Answer 6. Okay. So now just need to plug all of this into the formula that we have, right? So you will have CS equal to log to the base 2 of 1 plus SNRC اللي هي 1.995 minus log to the base 2 1 plus 1, right? We know that this is definitely gonna be 1, and this is the log of 2 to the base 2, and please use your calculator to tell me what's the other one. أي حد طلع 1.58. So the result is gonna be approximately
1.15.
ها؟
لا التوتال.
لا لا 0.58 بس مطروحين هم 1.58 minus 1, right? So yes 58, okay, 2 or whatever extra, okay. This quantity اللي هي the capacity that we get from this expression, remember this expression does not have the bandwidth here, so we don't have the bandwidth, right? So this expression is rate per hertz, so it's actually in bits per second per hertz. So for each 1 hertz of the channel, I have this amount of bits that I can transmit, bits per second, and if I increase the bandwidth, the rate that I can transmit becomes larger and larger and larger. تمام? Okay. But again, the units are not important, but you have to keep in mind what are the meanings of the things that we are getting out there. So this is a normalized capacity. This is the rate that I can transmit if I assume that I'm using only 1 hertz of the channel. Okay? And there is something called channel use, which is basically when you multiplex or when you add up more frequencies, we call that channel uses. So sometimes they call this bits per second per channel use. Okay? And you can increase your rate either by adding more frequencies or by multiplexing more users into the same channel within the same duration of transmission. So if you add more signals within the same, effectively you are increasing your rate, right? Within the same time duration, okay? Anyways, this is the final expression. My question was going to be, if, just a follow up on this, if Alice is transmitting to Bob at a rate of course it's an easy question, but you have to keep it in mind, right? 0.7 bits per second per hertz, right? Do you think that her communication is secure?
كيف 0.7 how is 0.7
يعني هبعت لما مثلا اكومينيكيت with يعني ايه 0.7 قصدك ازاي 0.7 بتس يعني ما كل الحكايه انه لما اقول 0.5 بتس معناه ان انا هبعت بت كل 2 seconds. That's 0.5 bit per second, right? So if it's smaller than 1, it means that I take more than 1 second to send 1 bit. Okay. Now, if this is the communication rate that Alice is transmitting to Bob, is this secure?
No.
Why?
It's more because this quantity will be less than 1. So
Which quantity?
Log 2 1 plus like the first CC, the channel capacity of Alice and Bob.
Okay.
It will be less than 1.
Yes.
So when you minus 1, it will be negative.
Yeah. Or simply, right, you can just say that this communication rate to Bob is less than the secure rate. Sorry, it's greater than the secure rate, which means that it's not secure. Because if you try to send at a rate higher than this, right, you will not achieve secure communication. That's the meaning of secrecy capacity, CS, right? So either what you described, because you took it back to the derivation, right? And you said, if I plug here 0.7, This means that 0.7 minus 1 is going to give me some negative number, which means there is no secure communication. Or you just have here the upper limit on secure communication. You cannot communicate at any rate higher than this and maintain security. And since she's communicating at 0.7, just compare this with this. Greater than, then it's not secure. Less than or equal, then it is secure. Okay? خلاص؟
less than secure.
هكتبها لكم. تمام؟ This at a rate of R equals. وأنا هقول لكم هنا if R is greater than secrecy capacity, no security. Okay? If R is less than or equal secrecy capacity, you can have security. تمام؟ I'm done with this part. تمام؟ I just want to discuss with you symmetric channel. What are the other variations that I can give you? يعني احنا عندنا binary symmetric channel, this one. Of course, what I will mention here is not all the possible variations, but to give you some idea that things can change. Yeah. Okay. So I can have, remember the binary symmetric channel P, P, and then 1 minus P, 1 minus P. Okay. Now I can have a non-symmetric channel. So binary non-symmetric channel, which means what?
The 1 minus p and
Yeah, so I will have here P1, I will have here some other value P2. وهتبقى this one is 1 minus P1 و this one is 1 minus P2. Sorry, which 1 minus P2. لا صح. Yeah, 1 minus P2, 1 minus P1. تمام؟ In this case, what does it mean يعني لما تبقى مش symmetric معناها this channel you can make errors from 0 to 1 with a probability different from if the transmitter was sending a 1. In that case, the error has a different probability. The channel, for example, is more reliable when you communicate ones rather than when you communicate zeros. It can happen, okay? So that's one variation. Another variation is going to be something called the binary erasure channel. I don't have this. So one of the two symbols always is going to be transmitted correctly. And the error can happen only in the other symbol. Okay? Or I can have something non-binary. So a channel that has, for example, ternary symmetric channel. Right? So you have still symmetric. So you have the same P here, the same P to make error here, to make error here, correct here, error, correct, error, error, right? All the errors will have a probability P, 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 right? But in this case, remember something very nice, okay? What's gonna be the probability of correct for each one of those? Then now we have 0, I can send also value 1, I can send value 2. I have some source that produces 3 different symbols, huh?
1 minus 2p.
Exactly. So the error, the correct here is gonna be 1 minus 2p. تمام? 1 minus 2p. Because I have p or p for errors, then the correct is 1 minus the sum of those two. تمام? 1 minus 2p. And then you can solve also for this, following exactly the same that we did for the others. Okay? So these are just some ideas of variations. There can be other variations. I can play with this channel the way I like. Yeah. Okay?
Don't play with it.
Don't play. Okay.